Assalamu alaikum, my dear student. I hope you are fine and doing well. Today class is about factorization and discrete law. Before going into the today lecture, I would suggest that why we are going to study factorization and discrete law. Because factorization is fundamentally utilized in public key cryptography. In factorization problem, we have to basically divide our some composite number into a prime factorization. So in that case, dear student, the factorization, based on factorization, we have some crypto system like RSA, Raven, and Pilar crypto system, and there are some other what you call the variant of integer factorization based crypto system. And in addition to that, the discrete log based problem is another fundamental problem in public key cryptography that is based on discrete log. So generally the log is based on we have calculate log in real number and log in real number we have some fraction values, but here in cryptography we need log our integers. It means whenever we are talking about discrete log, it means to say we have to talk about finite groups, and moreover it's a special type of groups. It must be cyclic group. And the students cyclic group have one or more than one generator. So in that case, we can say discrete log base is fundamentally uh, calculated for a cyclic group, and there must be a one generator. So let us come up with the today objective of our today class, and this fundamentally today lecture is basically consists of what you call these objectives will be covered in 3 or 4 lectures, which are will be the continuation of rest of our previous lectures. So today we will discuss objectives to discuss factorization algorithm and their application in cryptography. Means to say factorization, mainly we will discuss what does factorization means and what does integer factorization means. Then we will discuss CRT, Chinese remainder theorem, which are also very useful in RSA, Ravizit-Shamir Edelman algorithm. Then we will discuss quadratic residue and quadratic non-residue. And then at the end, we will discuss modular exponentiation and logarithm. And means to say, we will discuss discrete law problem. So integer factorization basically is the subject of continuous research in past, and so in that case, dear student, we will discuss first of all in one topic. In that case, fundamental theorem of arithmetic. That theorem basically tell you how you can write any composite number like what you call it as a like this one. Uh, like this one in any composite number as a product of prime or power of power of prime product power of prime means this is p1 p2 p3 are prime. So if e1 e2 e3 are some non-integer some integers, so non-negative integers, so if E1, E2, E3 all are 1, then in that case we have one case, and if these are not 1, then it means that any composite number can be written as a product of power of primes. And another definition, greatest common divisor and least common divisor. We have already discussed these definitions, so I am not going into the um, depth of this definition. You have to see all these these two definitions. Uh, let us integer factorization problem in cryptography. Like we have problem given a composite number and find its prime factors. It means if you have prime like p and q, it is quite easy to calculate n with the product of p and q, but it is quite hard to calculate n from what you call the from if you have n, then it is quite hard to calculate its prime factorization p and q. So it is one of the hard problem in cryptography that used in RSA type public key crypto system. Uh, Let us take some trivial examples. So that 1233 can be written as like this one. In that case, P1 is 3 and P2 is 137 and E1 is 2. So similarly, if you can look over here, dear student, 152 double 3 5 double 7 8 7 can be written as a product of power of prime into product of prime. So another one, like let us, dear student, our problem here is Chinese remainder theorem. Uh, the question arises why we are going to study this Chinese remainder theorem. Dear student, it is quite important because in our coming lectures, like in public key cryptography, we can use this Chinese remainder theorem in RSA calculation, and moreover in Rabin crypto system and other like Pilar crypto system. So that theorem basically is our numeric computations. So before starting Chinese remainder theorem formally, we have to discuss the one of the uh, Chinese scientist who devised this theorem, the Sun's tube problem. That problem basically states that there are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. When divided by 7, the remainder is 2. What is that number? That actually when divided by 3, it's remainder is 2, and when divided by 5, it's remainder is 3, and then divided by 7, it's remainder is 2. So question arises that what is the fundamentally the value of x like this one. If you can look over here, x is it must be congruent. Here I'm written equal, but it must be congruent. X is congruent to 2 mod 3 like this one, and x is congruent to 3 mod 5, and x is congruent to 2 mod 7. So in that case, the remainder is 2 when mod divided by 7. In that case, remainder is 3 if divided by 5, and remainder is 2 if divided by 3. So this is one of the problem that basically give the idea of Chinese remainder theorem, and in that corresponding to this problem, basically we have three problems. So we have to solve this three problem under modulo under one modulo problem. So I means to say this is P M1, M2, and M3, and we have to solve these three problems under mod uh, M. Like you have a number of like troops, there are scattered randomly. So how many people? I mean to say, what is fundamentally X? If you divide these troops into a if you divide into a class of 4, troops like this: 1 2 3 4, 1 2 3 4, 1 2 3 7, and the remainder is 3. These are remaining troops. In that case, x is congruent to 3 mod 4. If you divide this into a 5, like 1 2 3 4 5, and if you divide into a 5, that's it, and the remaining troops are 4. So x is congruent to 4 mod 5. In that case, what is actually x? I mean to say, what is total number of troops in that case? So Chinese remainder theorem, basically the idea how one can calculate such problem, how one can find the solution for such problems. So Chinese remainder theorem ultimately help us to find such problem. So let us formally take Chinese remainder theorem is used to solve set of congruent equation with one variable but different moduli, which are relatively prime as shown below. That is, x is congruent to a1 mod m1, x is congruent to a2 mod m2, and then so on, x is congruent to a2 mod uh, mk. It means to say Zm is congruent to Zm1 into Zm2 into Zm3 into Zmk. It means you have here number of set of equation under different moduli like m1, m2, m3. All these m1, m2, m3 are relatively prime to each other. Then m1, m2, m3 are primes. So I have basically this problem. This problem is place in that side. So I have to, since this is isomorphic, so I have to solve this system of equation in congruent mod m1 m2 in one modular under mod m. So this is the basically the idea of Chinese remainder theorem. So this is one of the hard problem, like there are system of equation, and under different moduli you have to solve it in this Zn under one modulo. So like let us take one simple example in order to understand what does it means. Following is also a set of equation with different one. X is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Find x for these conditions. What is the x that satisfy all these conditions? So let us take one graphical representation. So say you have numbers that you have to arrange in 3 rows, and the remainder is 2. So x is equal to remainder is 3, and you have to arrange the numbers into 5, like 5 rows: 1 2 3 4 5, and the remainder is 3. And say here the remainder is 2, like this from this equation, and you have to arrange the all element in 7 rows: 1 2 3 4. So x is congruent to 2 mod 7. The solution to this equation is given in next section. For the moment, we'll have to answer x is 23. X is 23, it means to say if you put in place of x, 23 is congruent to 2 mod 3. If you divide 23 by 3, then you will get 2. And if you divide 23 by 5, you will get remainder 3. And if you divide 23 by 7, then the remainder will be 2. In that case, the value of x will be 23. So Chinese remainder theorem, find m is equal to m1, m2, m3 up to m. These is a common moduli m. So find m1. M1 is m divided by m1. Capital M2 is capital M divided by m2, and so on. Mk is equal to m divided by mk. To find the multiplicative inverse of each m1, m2 using the corresponding modulo m1, m2, I call it inverses. And solution to simultaneous equation is this one, like this. So you have this problem, different problem in different moduli. So you have to solve this under same modulo m. That is the basically multiplication of this one, like this. This is our previous example. So in previous slide, we just make a hit and try, but here we have to use Chinese remainder theorem in order to properly get the answer. So first m is 3 into 5 into multiply these modulo 3, 5, 7 and get capital M. This is 105. And M1 is 105 divided by 3, which is 35. M2 is 105 divided by, and so on, and 3. So inverse of 35 uh, under mod M1 is like you have to under mod 3 is 2, and inverse of m2 under mod 5 is 1, and inverse of m3 under mod 7 is 1. So in that case, x is 2 into 35 into 2 plus 3 into 21 into 1 plus 2 into like this one, and take it mod 15, and you will get 23 mod. And this is basically the x for which this equation will be satisfied. These are some examples that you have to solve it by yourself. And again, I left this as an exercise. So another topic which is quite important while discussing public key cryptography, it is quadratic residue. Uh, Dear student, why we are going to study this? We are basically going to study a quadratic congruence or quadratic congruence classes, because this kind of basically definitions or this kind of concept will be quite fruitful in while designing public key Raven crypto system. So, dear student, the quadratic residue is generally is of the form this one. So we limit our discussion to the quadratic where a2 is 1 and a1 is 0. In that case, our quadratic residue will s square is common to a mod n. So in this section, we will discuss quadratic residue mod prime and quadratic residue mod composite number. So let us take first quadratic residue modulo prime. So what does it mean? First of all, we have to what you call so the equation x square is congruent to 3 mod has two solution. X is congruent to mod 5 mod 11 and x is congruent to minus mod 5. But note that minus 5 is congruent to 6 because there is no negative number in modulo 11. So the solution are actually 5 and 7. So these are two incongruent solutions. So let me give you another example. X square is congruent to 2 mod 11 has no solution. You know why, dear student, there is no solution? Because there is no such element in mod 11 for which we take square root of 2 and give us the result. So there is no such x in Z11 for which this equation is satisfied. So let us take another example. Quadratic residue and non-residue. In equation x square is common to a mod p, a is called quadratic residue. If it has two solutions, a is called quadratic residue, and if it has no solution, then in that case it is called quadratic non-residue. So let us take one example. there are 10 elements Z, multiplicative group Z, LM static. Exactly 5 are quadratic and half are quadratic and half are non-quadratic. So in Z11 static, these are quadratic and these are non-quadratic elements. So basically, you can say this equation is not satisfied for these element, and this equation is basically satisfied for these equation. So, dear student, if you can put so under root of 1 is again, if you can say any number x from Z11, under root of 1 is 1, so a is a. Don't mix this with x. So from here in x, you have to insert all the element of Z12, for which it has some what you call the square root exists. So in that case, if I can say quadratic residue of what you call, if I can place 3 over here. So in that case, dear student, the quadratic residue will be exist for 3, because 3 3 square, if we can put over here 3 case of x, you can say under root 3, x is equivalent to under root 3, and this under root 3 is basically, you can put over here 9. So in that case you will get 3, and this plus minus 3. In that case you have two solution for that. So it is quite easy to calculate whether certain number in modulo classes is quadratic residue or non-residue. For that, dear student, we will use Euler criteria. So it will be quite easy to determine whether these certain numbers are quadratic residue and non-residue in modulo class. Like Euler criteria tell us if a to the power p minus 1 divided by 2 is congruent to 1 mod p, then a is quadratic residue mod p. If this is equivalent to minus 1, then in that is the non-quadratic. Like to find out 14 or 16 is a quadratic residue in Z23 static, we calculate 14 to the power 23 minus 1 divided by 2. In that case, this is 22 mod 11. So in that case, this is one lesser um, than mod 23. In that case, this is non-residue. This 14 is non-residue. 16 to the power 23 minus 1 divided by 2. In that case, we will get 1. So in that case, 16 is quadratic residue under mod 23. So solve quadratic residue mod f. So we'll take special case p is equal to 4k plus 3. In that case, x is congruent to a to the power p plus 1 divided by 4, and x is minus a to the power p plus 1 divided by 2 mod p. Dear student, if you want to learn this equation from how we can get this equation, we will discuss this equation in while discussing Rabin crypto system, the complete derivation of this. So for that, I leave it as an exercise, and you can see this equation in um, one of the book by Doug Stinson, Cryptography, Practice and Theory by Doug Stinson. So, I left this example as an exercise. Dear student, let us take another what you call the uh, case of quadratic residue, mod a composite number. Previously, we will discuss quadratic residue under mod p, and here we will, like this, x square is congruent to a mod n. Here n is the what you call the product of primes. So in that case, dear student, we have solved this equation under mod different P1, P2, like Pk, and in that case, dear student, we have like if we can take its under root, then we will get b1 plus minus b1 plus the under root of a is plus minus b1 plus minus b2 and plus minus b3. In that case, we will use Chinese remainder theorem in order to get the answer for these values of x. Like assume that x square is equal congruent to 36 mod 70. We know that 77 can be 7 to 11. So, dear student, we have to decompose this x square is equal to 36 under mod 7, which is x square is congruent to 1 mod 7, and x square is congruent to 36 mod 11, which is the student 3. In that case, the answer will be x is what you call 1 and x is equal to minus 1. And in that case, x is equal to 5 and x is equal to minus 1. Now we can make four system of equation out of this. X is plus 1 mod 7, x is plus 1 mod 11, and similarly for with plus and with negative sign we have what you call the four equations for each. So in order to get this answer, x is plus minus 6 and x is plus minus 27, dear student, once again we have to use Chinese remainder theorem for uh, these system of what you call the modular equations. So congruent equation. So we will definitely get two answer from this equation, these relations, and two answer from these relations. In that case, we will have four different what you call the solution, and it has surely four different solution in that case. Dear student, while discussing complexity, so it is quite important to discuss in the paradigm of cryptography that solving a quadratic congruence modulo a composite number is same as the factorization a composite integer. As we have seen, if n is very large, the factorization is infeasible. Infeasible, I mean to say, through existing computational strategy, you cannot find such a what you call the very the factorization of very large number, composite number n. So we must note that solving a quadratic congruence mod a composite is as hard as factorization of modulus. So, dear student, this is what you call our lecture about Chinese remainder theorem, factorization. These are just ideas, and we will surely implement all these theoretical ideas in our crypto system, mainly public key cryptography. Till then, dear student, Allah Hafiz, may Allah bless you all, and please stay at home, and Allah Hafiz.